Hello guys, and welcome to the second part of this session about interrupts. Before diving into the code, I'd like to take an overview on the two chips 8520, also known as CIA. Despite I want to give you more details about these two chips later in this video, for this moment I'll talk about the registers involved for the keyboard handling. Every time we press a key on the keyboard, a 8-bit data is sent to the SDR. This register can work in input or output mode by handling bit 6 of CRA. On input mode, any input that comes from the keyboard, a key pressed for instance, generates a level 2 interrupt. We can get the code of the key pressed or released by reading the SDR register. To complete the handshake required to signal the keyboard that the Amiga has received the key code and is ready for the next one, we must switch between output and input mode in about 90 microseconds. The interrupt control register is also involved on keyboard handling. Like the DMA control and the antenna, it uses the most significant bit as a controller for the other bits. For a correct keyboard handling, we must ensure these two bits are set, otherwise we can exit the interrupt prematurely. Remember that when reading from these address, the register resets its value, so we can no longer read from there. We can now switch back to our keyboard interrupt handling and see the key points. On the first part of the interrupt, we read the bit 3 and 7 of the interrupt control register to understand if it's a request generated by keyboard event. As a good practice, we check the bit 3 of the interrupt request. And here we capture the key code from the serial data register. Since data is sent with the most significant bit placed at first position, we must roll the byte. We scan the key code, and if it's valid, we store in memory. After this, we can start the handshake with setting the serial port with output mode. In order to complete the handshake, we must wait at least 90 microseconds. This wait can be accomplished by using the CIAA timer or waiting for at least 3 raster lines, like in the example. Now I'll press F1 and see if the registered key code is the correct one. Good. Let's do another try with the A button. Okay, now let's talk about the CIAA and CIAB with more details. Each CIAA consists of 3 timers: Timer A, Timer B, and Time of the Day. More specifically, the CIAA has already reserved the timer A and B for some system tasks. The Time of the Day unit tick is based to the vertical synchronization of the screen. The interrupt control register allows the setting or unsetting of the CIAA functions. The control registers A and B allows to control the relative timers of the CIAA. The bit 7 of the control register B is reserved for setting the time of the day clock alarm. The serial data register, which we have already seen for the keyboard handling, is only used for the CIAA. For the CIAB, you may notice that the timer A and B are not used by the system, and the time of the day clock is synchronized with the H-sync rate. Thus, its tick duration is faster than its brother. By the way, I don't recommend to use the CIAA Timer B, especially if you don't want to have unpredictable results after returning to the system. Before loading the examples, Let's have further details about timing and frequencies. On this example with timer A, we'll prove that by setting a time value of about 450 ticks, from the start of the timer A, we will count about 10 raster lines at the underflow event of the timer. After running the test, we'll check how many lines passed before the timer finishes count. And yes, the output corresponds to the expected value. Let's see an example now of the timer A one-shot mode set, and an interrupt triggered when it's underflow. We'll set a timer value of about 550 ticks, which equals to about 10 raster lines. For register A, we disable everything but the one-shot mode. For app control register, we set the timer A as enable. A and B are timers of 16-bit precision. Therefore, we must set the low and high byte. You may notice that this instruction can be actually avoided, because in one-shot mode, a write to timer high will initiate the counting regardless the start bit. Let's run and see if the interrupt is triggered. The variable on memory is updated, so it's okay. Let's open an example of timer A with continuous mode interrupt. I set this time value so the interrupt should be triggered each vertical blank. The interrupt contains an instruction that increments the memory content by 1. I can do better result with being more accurate. After 1 second wait, the counter should have reached a value of about 50. Let's open an example of the time of the day clock now. Remember that the clock tick duration differs between the two chips. TOD time has a 24-bit precision, so we must set 3 bytes for the time. By setting the lower byte, the TOD will automatically start the timer. Since the timer increases its value from the start, we want to match the target value before exit. By reading the high byte, we also latches the timer value. Latching function ensures that reading the TOD value keeps consistent through the next read from the lower byte registers. Let's have an example for better understanding. This is an hypothetical snapshot of the timer read at a certain moment. When executing the next instruction, the timer value changes. However, thanks to the timer latching feature, I will get a consistent time value. By reading the timer lower value, I also release the timer latch. The CIAB settings are basically the same. I only change the target match value because of the different tick duration. According to the different target value for each clock, these are the expected seconds to wait before the timer finish. Okay, let's do the same for the CIAB clock. For the final example, I want to attach an interrupt that is triggered by the clock's alarm event. Here you can see I've mapped an interrupt of level 2 to my custom routine. For setting the alarm, I set the bit 7 of the control register B. I set the alarm with the desired value. I enable the alarm on the control interrupt register. Now that the alarm is set, I can clear the bit 7 of the CRP. Then I can finally reset the clock value to 0. By setting the lower byte, the timer will start. On the interrupt, we must read the interrupt control register, otherwise we would get into an infinite loop. Remember that interrupt of level 2 and 6 are external interrupts, so they are also requested by other peripherals. With this instruction you are aware that it's actually an alarm event. I want to move this value in memory just as a proof of concept. Indeed, I expect to pass on this instruction only when the alarm will trigger the event. Now I'll stop before the 5 seconds are passed, and the memory is still clear. This time we can see the interrupt was correctly triggered. As a fine example, I want to show how to catch a keyboard routine of a famous game of Amiga. With the support of the tool Action Replay, I will replace the button F10, which is currently used for exiting the game, with the button F9. We can see the interrupt of level 2 is currently mapped to a custom routine. The key code is saved at this memory address. By using the command find address of Action Replay, I want to find all the instructions that scan the memory content in which the key code is stored. We can see there are many checks on the F10 button, most probably one for each state of the game. I'll take the first result and change the key code 59 with 58. Okay, let's press the function 9 button and see what happens. And yes, I forgot to remove the breakpoint. Okay, I quit the game prematurely, so the test was successful. That's all about interrupts for this video. Hope you find somehow interesting, and if you liked it, please subscribe. Thank you, and see you on next video.